Okay, how's everybody doing today? My name's Ronny. Jeanna Matthews couldn't make it today. She's my PhD advisor at Clarkson University. This is work I'm doing for my PhD dissertation. It's Layer 2 Network Security in Virtualized Environments. Okay, so a little bit about myself. I'm a computer science PhD student at Clarkson University. I'm also a full-time lecturer at the SUNY Polytechnic Institute in New York. I'm also a software engineer for Axelis Inc. Out of AFRL in Rome, New York. And I'm also the owner of a consulting company called Adirondack IT Solutions. Dr. Matthews is an associate professor for the Department of Computer Science at Clarkson University. Okay, so I'm going to basically go over the abstract of my research, talk a little bit about virtualization, just a brief overview, talk about multi-tenancy, and then go over some virtual networking options like bridging and switching. Then talk about some layer 2 network attacks, which most of you guys should probably be familiar with already. Then I intend to give a demo. Hopefully that'll work out well for us. Discuss my results, and then hopefully we'll have some time for discussion. Okay, so cloud services. Everybody's probably heard of cloud services by now. Most likely everybody in this room is using some sort of form of cloud services. Specifically, I'm looking at multi-tenant environments for virtualization. So these are virtual machines that are typically all connected to a single virtual network device within a single host. These things could be using a virtual bridge or a virtual switch, depending on the environment. And these are just software emulated versions of these physical devices. So the question I've posed is, since all client virtual machines are essentially connected to a virtual version of a physical networking device, do typical layer 2 network attacks that work on physical devices apply to their virtual counterparts? So can we use things like MAC flooding, VLAN hopping, and whatnot to actually infiltrate these virtual devices? So it's an important question to explore because all services that are in the cloud that rely on virtualized environments could be vulnerable to these attacks. And this includes data centers hosting, client-sensitive data in their environments. So let's look at a hypothetical case here of Coke versus Pepsi, two rival cola companies. What if they hosted their data services at the same provider? What if these virtual servers were co-located on the same host? And what if there was a fairly easy way for one to gain a competitive edge over the other? Okay, so basic overview of virtualization. We have a bunch of physical servers and we consolidate them to a single host with a lot more resources available to it than the actual other machines, giving us energy cost savings, giving us a better efficiency on our resources and utilization of our resources than we typically would have. So in this case, I have a web server, email server, file server, and application server, all consolidated down to this larger virtualization server. If we take a look at the inside of this box, we can see that the host OS would have 32 gigabytes of RAM, maybe 16 CPU cores, and then we see that all these machines are stuffed inside of it, each taking a little slice of those resources that are available from the machine. So at SUNY Poly, we have this centralized virtualization environment that we use for our school. So dorm users, computer lab users, and remote users can all access their environments within this single server, allowing them, access from all across the campus or outside the campus or whatnot, all in a centralized environment. And we have a heterogeneous mix of systems that are on there. This is different from decentralized virtualization, which a lot of people are used to with VirtualBox or VMware, where you actually have your own host, your own system, maybe a laptop or another physical, larger computer that's hosting virtual machines. So it's more isolated than actually a centralized solution that has many people using the same system for their virtualized machines. So multi-tenancy is basically cloud service providers are trying to maximize their resources. So what they're going to do is they're going to take a bunch of VMs from a bunch of different clients, stick them on one box, and pretty much try to use all the resources that they can off that box until the box becomes saturated. They may even overextend things by using something like thin provisioning for drive space or whatnot. And these are heterogeneous environments, so they have different operating systems running different services. So we could have Linux, Windows systems on this environment. We could also be running web services, FTP services, application servers, or whatever. But client access to the VMs vary. So some of them give you full root privileges. If you go and grab an Amazon EC2 instance, you can actually, set up your own VM, install everything from scratch. They give you full root access. Some of them actually give you pre-canned templates. Some may restrict what you can do with it. Maybe they give you a VPS. They just give you a shell with restrictive access so you can't get root or whatnot on there. So here's just a couple examples of multi-tenancy service providers. We have Amazon EC2, Microsoft's Azure, Google Cloud Services. And then there's a bunch of fly-by-night VPSs out there. If you just Google virtual private server, you're going to find tons of different environments out there. Brick and mortar data centers, so most of you are probably familiar with someplace maybe in your local area that's hosting for local clients or whatnot. And they have all the local area clients host on virtualization servers in their environment and their server racks, all connected to the same physical network. Maybe some of them are competitors of each other, but they're all hosting in that same area. So the similarities of these is some are running some form of open source Xen or Xen server. Some use VMware or Hyper-V, but all of them share a single network connection between the tenants, right? So they're all on the same physical host or maybe multiple physical hosts, but everyone on that single physical host is all connected to either a virtual bridge or a virtual switching device. So here's just a kind of an overview of multi-tenancy. We again see our host OS with 32 gigabytes of memory, 16 CPU cores. In this case, I've shown Coke and Pepsi. They both have web servers. They both have some DNS servers on the same host. Maybe an application server. We see Pepsi has an EDI server on here where, maybe they're dealing with their trucking information, or their customer base information. But the idea here is that they're all hosting on the same physical server, hosting their virtual servers, and all that information is sitting there on the same physical hard drive space, using the same Ethernet physical adapter going out to the physical network, and maybe it's just, bridged or it's switched. So here we're seeing two physical network interfaces. One is dedicated for the host OS for administrative purposes, and the other one's actually dedicated for the virtual machines to use to get out to the physical network. Now, what I don't show is here, we would have some sort of virtual switch or a bridge that those machines are connecting to that actually is bridging over to that physical interface. Okay, so we'll just talk a little about bridging. Physical bridges connect two or more layer 2 network segments. They're going to separate collision domains. So we should have some sort of isolation of traffic. They maintain a MAC address forwarding table for each of the sides of the segment. So basically, if some machines are over on this side of the segment and some machines are over on the other side of the bridge, if a machine on one side of the bridge wants to send a packet over to another machine on that same side of the bridge, it won't cross the bridge in order to make the communication. But if it wants to send a packet over to the other side of the bridge, then that packet has to cross the bridge to get over to the other side. This is based on the MAC addresses in this table. So here's just a basic image of that. We have 3 on one side, 3 on the other. We can see the MAC addresses. So if that top machine over on the one side wants to talk to one on the bottom, it's not going to cross the bridge. It's just going to hit that side. The bridge is going to say, oh, look at my table. I see the MAC address is still on your side, on your segment, so we're just going to keep that, that network traffic on that side of the bridge. Otherwise, we'll travel over to the other side of, say, the top machine wants to talk to the middle machine on the other side. Then we traverse the bridge to actually make that communication happen. So virtual bridges are the simplest form of virtual networking. They use 802.1d Ethernet bridging, which is built into the Linux kernel. And then we use this user space bridge utils package in order to actually work with those bridging, the bridging kernel driver. It uses a virtual tap interface to connect these machines to the virtual bridge. And this is just basically a user space network tap. It's simulating that layer 2 link layer connection between the machines and the actual networking device. So here I've inserted the virtual bridge. In this case, it's in Xen World. It's called BR0. And we have the tap interfaces on each of the virtual machines that's connecting to that bridge, which eventually gets them to that physical interface if they need to get outside to the real world or the physical environment. But they are all connected to that physical bridge, and we're seeing separate individual network segments here. So this differs from switching, because switching does operate at layer 2 or higher. It's not just layer 2 like bridging. Switches are considered as multi-port bridges, as we all probably know in here. And they do separate collision domains. Each port on the bridge is its own little collision domain. The big thing that separates switches from bridges is we have a CAM table. And this CAM table is called content addressable memory. It's similar to the forwarding table we see in bridges. However, basically this is a dynamic table that maps the ports to the MAC addresses of the machines that are connected to that port. Now, we could have multiple MAC addresses assigned to that port because we could have switches that are daisy-chained to each other, so that port should know about all the MAC addresses that are basically, uplinked to that one single port, daisy-chained off to the other switches. So this allows the switches to intelligently send traffic from one port to the next based upon what MAC addresses are connected, so that, we're not broadcasting that traffic across the whole entire switch, as in the case of a hub. Really, what the switch needs to do this is it needs to check the frame header information of the Ethernet frame going across the network for that MAC address, and then forward the traffic based upon that MAC address after it looks at its CAM table and says, okay, this is on this port over here, this is on that port over there. But the big thing to note here is that switches are embedded devices, and they only have a finite amount of memory available to them. So once that CAM table fills up, it ends up going into a hub mode or a fail-safe mode, which ends up basically dumping all the traffic to every connected device. So here I just have a picture of an Ethernet frame, and we see the preamble and the destination address, which is abstracted out. And that's basically what the switch needs to know in order to actually forward that traffic on. And we do have cut-through switching and stored forward mode, but really both of them need to know what that destination MAC address is in order to complete the activity of sending the network packet. So here I just show a switch. I have a few machines connected to different ports, and we can see the MAC addresses up on top there. We can see it's just basically a CAM table. And we have one MAC address pointing to port 2, one MAC address pointing to port 7, and so on and so forth. So if the machine at port 2 would like to talk to the machine at port 14, basically it sends out the packet, the switch strips out the frame header, looks for the MAC address for the destination, matches it against its CAM table, and then sends the packet accordingly across the switch to that single port instead of flooding all of the ports, the traffic across all the ports so all the machines can see it. So virtual switches are an advanced form of virtual networking. Just like their physical counterparts, they can deal with layer 2 or higher information depending on the switch and the capabilities of that switch. So we can do things like QoS, VLAN configurations, performance monitoring, and so forth. Content filtering if we get as high as an application layer switch. And they all connect similarly like a bridge where we're using those virtual interfaces to connect the devices to the actual switch themselves. So here we see I've replaced that bridge with a virtual switch, in this case ZenBR0, and we see the virtual interfaces for each of the machines. The virtual machines on that host environment are connected to that virtual switch, and then they're all connected to that physical network interface that go out to the physical network. So there are a variety of virtual switches available. Typically these are associated with some sort of different hypervisor environment. We see Open vSwitch is usually on Zen environments, or Citrix Zen Server uses this by default. KVM environments, and Proxmox is another hypervisor that uses Open vSwitch. The Cisco Nexus 1000V series is a VMware vSphere add-on switch, and you can also use this in the Microsoft Hyper-V environment. And then there's the Microsoft Hyper-V Virtual Switch, which is the default virtual switch for the Hyper-V environment. And then if you look at ESXi for vSphere, they have their own default vSwitch available too. So the Nexus 1000V is just something you can buy separate or use the free edition to kind of incorporate that in. All of these are considered as enterprise-level solutions. So from Open vSwitch, which is the open source vSwitch, all the way up to the Cisco Nexus 1000V, they're all enterprise-level switches. So you would think they would have some sort of enterprise-level functionality or protection against some sort of attack. Okay, so basic network, layer 2 network attacks, MAC flooding. How many guys have done MAC flooding in here, in this room? Okay, a few people, right? It's pretty easy to do. You just run a command, just floods a network with a bunch of MAC addresses. What that does is it fills up that CAM table and forces the switch into a hub mode if it doesn't know how to protect itself against that. So then all the frames are forwarded across the network and everybody can hear what's going on that switch. You can start eavesdropping on traffic, replay packets, all that good stuff. This works well on most physical switches, and it's worked well for about 20 years on most physical switches. So this is something you would think would be fixed in the software version of a physical switch, right? When we go to emulate these devices, we could have looked at, all the vulnerabilities that were associated with them, and it should have been coded in to look for checks or whatnot to actually prevent this from occurring. This is typically mitigated on physical switches by using port security, which Cisco has embedded in most of their devices. The only virtual switch that offers this type of protection would be the Cisco Nexus 1000V, but the enterprise level one you have to pay for. The free version does not offer this protection. VLAN hopping is another layer 2 attack. Basically what you can do is take a frame that's, you take a machine that's actually plugged into a trunk port or a default VLAN, so it has access to multiple virtual LANs on that switch. And then what you can do is you can modify the VLAN tag on your frame and try to put yourself on one of those other VLANs, or the target VLAN you want to get on, rather than the VLAN you're currently on. So again, it requires access to the default VLAN or the trunk port, and it can be mitigated by strict VLAN configuration. So basically, any devices that are connected to a switch port that's configured as a trunk port or a VLAN, it shouldn't be. It should be just connected to a port that, is specific to that VLAN that device should be associated with. So again, mitigate this by strict VLAN configuration of the physical switch ports. DHCP attacks, so we could put a rogue DHCP server on a virtual network. If we had the main DHCP server was giving out addresses, maybe clients start associating to this rogue DHCP server, it starts answering the requests. So then they start getting these rogue services like DNS and TFTP. So what happens if we get associated with a DNS server that's actually poisoned? Well, now things like banking sites that I want to make look like real, but they're my site, and I got clients forced over to those. I'm capturing passwords or whatnot. so I can poison that DNS server. TFTP, if we got devices like soft phones or hard phones, in the VoIP land, hard phones usually pull their TFTP information based upon what they get from DHCP. So if we give a rogue TFTP server, what we can do is maybe put a malicious firmware onto that phone. This would be in the physical environment. And then that phone could be, sending packets out to some other destination so we can start eavesdropping on those conversations. We can also create denial of service situations by giving duplicate addressing on the network. So we can actually start blocking out services based upon that. So this can be mitigated by enforcing static addressing, but that gets really cumbersome in a very large environment. So when you're dealing with like 1,000 or 10,000 machines in an environment, you kind of rely on DHCP to actually push out all those addresses accordingly. Maybe you have some static addressing for your servers, but still, if you throw a different DHCP server on there and all your clients are grabbing DHCP addresses, some of those are going to associate to that rogue DHCP server. Then there's ARP spoofing. It's just broadcasting fake ARP resolution messages to a network used to hijack traffic, put yourself in a man in the middle to eavesdrop on traffic or manipulate the flow of traffic. This can be mitigated by using static ARP entries. Again, if you've ever looked at an ARP table on a machine and you're dealing with 1,000 or 10,000 machines, who wants to go around and modify ARP tables on every single machine to do static entries? It's just not feasible to do. So this is something that's hard to prevent. So let's look at a malicious VM in a multi-tenant cloud environment. Here we see the host OS with 32 gigabytes of memory, 16 CPU cores, and we have all the servers that were on there before, but now all of a sudden Coke throws a malicious app server into the mix, something that's actually going to start trying to eavesdrop on the traffic that Pepsi's generating. So here we see that that malicious app server is now connected to the same virtual switch as the other machines in that virtual network. So we can see that looking at the layer 2 attacks that I just discussed, something could happen here. We could try to do a MAC flooding attack on this environment and possibly start eavesdropping on all the traffic that's going across that network. Okay, so I'd like to give a little demo on this, and what I've done so far is I've actually done the MAC flooding attacks, and hopefully I can show you guys that here right now, and show you that this is actually effective in certain environments. So this is the SUNY Poly Cloud Security Research Lab. We actually have a dedicated server rack for this research. So here we have many different hypervisor environments in this rack. Just wanted to kind of show this to you guys that we actually had this really large rack here with a whole bunch of good stuff in it. So the first attack I'm going to show is a MAC flooding attack on a bridged interface using Gentoo Linux, open source Zen, and Linux kernel bridging. Then I intend to show a MAC flooding attack on virtual switched interface using Gentoo, open source Zen, and the latest Open vSwitch. And then MAC flooding attack on a virtual switched interface using Citrix Zen server. Show of hands, who thinks that the bridged attack is going to work? Okay, what about the Open vSwitch? And what about Citrix Zen server? Okay. So let's go up here and try this out. So we can see here, this is just using a Gentoo kernel, 3.10.7. And I've got a bridged interface set up on the second interface on this server, which is ENP4S0. Over on this side, each of these systems has 2 Kali Linux virtual machines on them. I have it labeled as Kali 1 and Kali 2. Kali 1 is going to be using links to actually just access the internet and just start surfing a web page. Kali 2 is going to be running the MAC flooding attack, and then I'm also going to be running TCP dump to actually sniff the traffic and attempt to capture that traffic. So let's see, I'm just running a screen session here. So I got a little script running on each of these that's just basically running TCP dump, and it's targeting, in this case, Kali 1, specifically by the IP address, and I'm just looking for HTTP traffic going across the network. So I'm just kind of filtering out for the HTTP traffic. We could see a lot more if this actually worked, if I didn't do that, and if I actually was going for the full network rather than just a single isolated machine. But in this case, we're just going to go for a target. Okay, so let me switch over to the... Okay, so I'm going to start running the MAC flooding attack on Kali 2, and this is going to start slowing things down. It's almost going to cause a denial of service because the network's just going to get so flooded from this. So here we go, we're just flooding the network. And then I'll start surfing the web. So if this were to work, we would start seeing traffic popping up on the sniffing interface here. And we're really not seeing anything happen on this bridge interface, which is to be expected, because what a bridge is doing is it has that forwarding table and knows what's on one side of that bridge and what's on the other side of that bridge. And if it's seeing all these random MAC addresses popping up, basically it's saying, I don't know where the hell to send those things. So what it does is it ends up dropping those packets, so they don't actually cross that segment. So bridge mode seems to be a fairly safe networking thing to use in a virtualized environment. So if you're using something like Citrix Zen Server or using open source Zen, I highly recommend using bridge mode. Okay, let's see what happens if we actually do this in an open vSwitch environment. So again, this is a Gen 2 Linux machine, so we'll just... And then if I do... Let me sudo up to that. We can see the virtual switch configuration here, just showing all the different virtual switch ports, the virtual interfaces, just to show that we actually have an open vSwitch configuration on the system. So over here, I'm going to go over to the Kali 3 VM, or CS3 Kali VM here. And we can see again, I'm targeting that first VM on this host, which I'm going to run links on again. And I'll run the MAC flooding attack again. Okay, so I did just try to switch there. It's a little bit laggy because the MAC flooding is working here. So let's just start surfing this, the web here on this. It may take a little bit of time. Of course, it's going to take a lot of time. Well, this one should actually work. Oh, there it is. It's a little bit laggy. But we start actually seeing packets going across, and it may take a little bit of time before we actually start seeing all the packets. But we should start seeing some source code for the web pages here. It's just taking a little time because of the... But as we can see that the open vSwitch environment is allowing us to actually see the traffic across the network here. And what I can do is I'll show oh, there we go, a little more. I'll show the video where it's actually really doing it after this. So as I'm just surfing the web here, we're seeing traffic from the other machine on this network. So that was the vSwitched environment. That wasn't the bridged environment. That's an enterprise-level virtual switch, and we're actually able to sniff the traffic once we start doing a MAC flooding attack. So let's look at Citrix Zen Server now. Now, Citrix Zen Server uses an older version of Open vSwitch by default. So you see it's using a Red Hat kernel here. And we can see the Open vSwitch configuration on the system. So in this case, I'm not going to target a single machine. I'm going to let it just ride on the whole entire network, and let's see what happens with that. I'm going to let it sit here for a little bit before I start doing links. It is a Saturday. This is on the school network. There's not many people there. But what I'm expecting to start seeing here is what happens, that I've found out what happens in the Citrix Zen Server environment is just that. I haven't generated any traffic on the virtual machine yet that I was targeting, but we're seeing that the actual MAC flooding has left the virtualized environment and is started to actually flood the physical switches. This is traffic on the physical environment. Now, I'm not showing all the information. I'm just showing the header information here because, I don't want to show other people's traffic because that would kind of be not legitimate. But we are actually flooding the entire network now with packets. So this is an enterprise level solution. This is the latest version of Citrix Zen Server, and I'm actually able to flood the network and start going out into the physical world here. Now, if I go back to my Linux version here, we're going to see that this starts working, but it takes a little bit of time because of the lag, because I am flooding the network like crazy. But eventually we should start seeing a kali.cs.sunyit DNS resolution here going to a spike.cs.sunyit.edu, which is hosting my web page here. There it is right there at the bottom. So we just saw the traffic from that virtual machine. So not only was it effective in getting the virtual machine traffic, but it was also effective in getting other client VMs. When I first did this, I was kind of running this flooding attack, and I had a couple students in the lab connected to the physical switch that the server was connected to. They were doing some lab write-ups and stuff in there and searching the web a little bit, and I'm running the attack, and all of a sudden I see all their stuff fly up on the screen. I'm like, what just happened? And I went and I looked on the screens what they were doing, and I was sniffing their traffic on the physical switch. So this is kind of scary that we can actually do this. So I decided to actually start looking into other environments like VMware and actually Hyper-V environments to see how it worked on those different environments as well. And I found some other interesting facts based upon that. Kill this out here. So we see I killed the MAC flooding, but because of the delay, it's still kind of throwing up some information here, but eventually it does stop, and we don't see any more information passing through. Okay, so again, what if there was a fairly easy way for one to gain a competitive edge over the other? So if they were in a Citrix Zen Server environment or a Zen environment, we could see that we could sniff traffic between them. And a lot of these fly-by-night VPSs, they just run up, a regular open vSwitch environment running on open source Zen with some Linux distribution because it's free. So if you go and subscribe to one of these things and you put your information out in that environment, you may be susceptible to this kind of attack. Or even if they're using Citrix Zen Server, you may be susceptible to this kind of attack. Okay, so this is, I was actually doing this in Kali with Wireshark as well, and this is showing the results of the bridged interface. I just did it with TCP dump and links in this case because it's a little easier to do over SSH in a remote location. But it does work as well, just as well with Wireshark since TCP dump is just a command line version of Wireshark. So the bridged information, we see nothing really happens here. But if we do this with Open vSwitch, in this case it was 2.0.0, we see I was able to sniff all that traffic as I was actually running the attack. So this table shows the other environments I tested on. We can see that Linux bridging is not vulnerable. So if you're running a Citrix Zen Server environment, my recommendation is put it into bridge mode. You can do that in Citrix land. They do allow it. It's defaulted to Open vSwitch, but you can go into the configuration and change it over to a bridged environment, which will prevent this kind of attack. We see that anything using Open vSwitch is vulnerable to packet sniffing if you do the MAC flooding attack. Microsoft Hyper-V, I tried it on both the Windows Server 2003 full edition as well as the Hyper-V free edition, and I found, this was 2008, I found that it wasn't vulnerable. It wasn't because of the vSwitch. It's because Microsoft 2008 Server has built-in protection against MAC spoofing. And for some reason, that helps against this kind of attack because we're just basically spoofing a whole bunch of random MAC addresses, and Server 2008 protects against that. Go Microsoft for one thing, right? So it seems like a better environment in this kind of a case than using Open vSwitch, but performance-wise, half and half there. I can't really talk about the effects of what happened in VMware because their end-user license agreement prevents from talking about any performance or testing based upon that unless you get written consent from them, which I did not get. But I will say that Microsoft did base their environment heavily upon VMware, so take it as you will, test it on your own and see what you think. What was that again? I haven't tested with vShield running in the environment yet. I just tested on the basic default ESXi configuration. But that's a good point, and that's something I should look into. Thank you for that. So in conclusion, all layer 2 vulnerabilities discussed here were targeted towards the virtual networking platforms and not the hypervisors themselves. That's important to recognize here because I'm not targeting the hypervisors. I'm just targeting the actual networking that's going on there. And the results show that the virtual networking devices can be just as vulnerable to these types of attacks as their physical counterparts. So further research is going to be looking at these other attacks I talked about at the beginning here with VLAN hopping and ARP spoofing and DHCP attacks as I go down the line. But for right now, I was just looking at the MAC flooding to see if it was feasible to actually progress on to looking at this information. So Zen Server and other solutions using Open vSwitch are vulnerable out of the box default configuration. It's kind of scary. So if you're a network administrator out there and you're putting these things in just blindly, just trusting that they've taken care of this stuff, you're kind of looking at false hopes there. You should really look at tightening these things up a little more. Maybe look at deploying something that's a little more secure than just using something as Open vSwitch. We could also look at maybe using something like software-defined networking. Open vSwitch does allow for that connectivity where we can actually start defining certain flows and specific flows and filtering traffic based on certain characteristics to start, preventing this kind of activity from occurring. But not everybody is really well versed on software-defined networking, and a lot of people just accept that default configuration. So a single malicious virtual machine has the potential to sniff all traffic passing across a virtual switch. And as I showed, this can actually pass through the actual virtual environment and affect the physical network as well, and start daisy chaining down the line through all the uplinks, taking out all the switches, which in turn breaks the VLAN separation as well, because we saw traffic that was not on the isolated virtual LAN that my server was on. We started seeing traffic from other virtual environments as well. So this is a significant threat to the CIA of any information passing over that virtualized network. So I'd like to thank a few people for this work. My PhD advisor, Nick Morani, who's here as well with his SUNY Poly DogNet student admins. They gave me a lot of equipment, rack space and stuff to use and allowed me to kind of wreak havoc on their network to do this research. I have Cloud Security Research Lab assistants, Dylan Long and Dan Spear, which helped me kind of set up this environment. My department chair, Chris Urban, which got me funding for some of the equipment and for some of the software we were using. The SUNY Polytechnic Research Foundation for funding some of this research, as well as SUNY Poly NCS Club, who's kind of here in strength to support this talk for me today. So with that, any questions? I'm sure there's a few questions in the audience here. Yes? So hardware-based virtual interfaces, you're saying? Yes, so the question was, what was the question again? I didn't hear the first part. Okay, so the question was SROD, if I could actually virtualize the hardware interface? Yeah, I haven't done anything with that right now, but that's something I will look into. Thank you for that. Any other questions? Yes? Yeah, I talked about brick and mortar. So you're talking about maybe, he asked about commercial data centers or just commercialized VPSs? Commercial cloud. I haven't tested this on Amazon EC2 or any of those other commercialized environments, but if they're using Open vSwitch in their environment and they're doing default configuration, then they're going to be vulnerable. But mostly some of those bigger companies are taking other precautions, like maybe they're using other higher layer appliances to look for this kind of traffic to prevent that. Maybe they're using something like OpenStack, which does use SDN to actually create flows so they can actually prevent some of this attack from occurring. But I haven't actually taken this out to the cloud yet, which I do intend to do eventually. But I know with Amazon EC2, you need to actually talk to them about what you're going to do on their environment. You can't just start pen testing their environment out of the blue. You got to kind of get their permission to do something like that. So that's something I do intend to look into. Anything else? Any other questions? No? Okay. Well, thank you all.